Hello everyone. Make sure everything's working. My name is Gabriella. Today we're working on exam 3, part 3 for transport 1. Basically what we'll be doing in this video is implementing our derivations of calculating the time varying temperatures of our uniform beam or bar of our temperature profile. And we'll be implementing that to show the transition from stable to unstable results at specific values of the discretization. Okay. So we're going to start by importing NumPy in our code. Basically, this allows us to do some fast mathematical operations, like use arrays, use some linear algebra in our code for our expressions and calculations. Come on. Next, we want to start defining our conditions and variables of our problem. So what we're given here is our uniform bar for our temperature profile is 50 meters in length, and we know that the finite difference with the spatial step size is 1 meter. So we know that we have a number of 5 or a number of 50 spatial steps with a thermal diffusivity of 1 meter squared per second. So for our thermal diffusivity, we're going to define that as alpha, and that's given as 1. Next, we want the number of length for our nodes, which is going to be 50. And then the number of time increments for our bar, which is going to be an arbitrary number, so we'll just put 100. And we'll use this number to test our expression in our calculations to see the stability in that. Next, we have from our last video the change in our nodes, our spatial divisions, our spatial steps, which is 1. I don't know what that is. And then the change in our time increments, which is 0.5. The next thing we want to define is our R expression that we got from our Crank-Nicholas method, Nicholson method, which was our thermal diffusivity as alpha times the derivative or the change in our time increments over the change in our spatial steps raised to the second power. Next, what we want to do is we want to define x as we want to create a range for our specific our spatial steps, basically. I'm going to use NumPy arrange for that. And this is basically just going to allow us to pick and choose a segment along the bar to calculate from. So I'm going to have our spatial steps times our change in spatial steps. I'm not sure what that means. We'll figure it out. Okay. We have all of our conditions and our variables. The next thing we want to do is we want to create an array for our bar with showing all of our temperatures. And we're going to do that using the np-fool function with the parameters of our spatial steps, the uniform temperature at 20 degrees Celsius. And then we want to define the left inside and the right inside of our bar. And we're going to do that by indexing 0 for the left-hand side. And we're going to set that to 50 degrees Celsius. And then indexing -1 for the right-hand side. And let's just set that to 80 degrees Celsius. And we want to run, make sure that's looking good. So now that we have all of our conditions set and we have created our array, we want to go ahead and check that that's looking well. All right, so yep, we have a 50 segment bar showing here on the left-hand side that we set it to 50 degrees Celsius, and on the right-hand side that we set it to 80 degrees Celsius. And then it shows a uniform temperature of 20 degrees Celsius all throughout. And it shows our 50 temperatures, so that looks good. And get that out of there and move on to our next step, which is to plot our temperatures into a graph before we do any calculations. So in order to do that, we need to import from plotly subplots, import make subplots. And then we need to import plotly graph objects as go. So basically, this is going to allow us to choose what kind of graph we want to represent our data. And so for our figure, we want to define that as make subplots. And so we're going to create a row of 1 and a column of 1. And then we're going to choose a scatter plot for our data. So we're going to big add scatter. We need to define our x-axis, and that's going to be our spatial nodes, and then our y-axis will be our initial temperatures that we need to calculate. And then we're just going to name our graph, give it a title of our initial, say initial for our initial temperatures. And I think that should, yeah. All right, so that looks good. We're taking a look at this graph. Looks very similar to our array. So we know that on the left-hand side, we heated it to 50 degrees Celsius. And then throughout the rest of the segments of the bar, we have a uniform 20 degrees Celsius for our temperature. And then on the right-hand side, it is heated to 80 degrees Celsius. So it looks like our graph is representing the data well. We can move on to adding in our expression that we got from part 2. For this, we want to create a range that will allow us to calculate our temperatures at each segment. For I in range, argument of 1, create an argument of 1, and then number of time increments. And then we're just going to go ahead and put in our expression we got from part 2. We're going to index that as 1:-1. to show from the left-hand side to the right-hand side equals t1 negative 1 again plus our expression times t2 minus 2 times t index 1 colon negative 1 minus t colon negative 2. So parentheses looks good. All right, so now that we have our expression in there, what we want to do is we want to graph our expression again to calculate our temperature at specific times. And just to make this quick, we can copy and paste this down here. And then we're going to add some lines into our graph representation. And then should be able to just show the graph in this. Oof! All right, I think that we have some indexing errors here because we've got a little zigzag in there and that does not look right. All right, I think I'm supposed to have I need to add. Oh no, does not look good. Gotta figure out why. Oh god. Maybe if I add this here. Just delete that mess. A lot of a mess right there real quick. No, I don't think that's right either. So I'm just gonna go back. Have this in its own function. I had an issue like this earlier. Where it creates just two. Yeah, so we have that graph, and then this is doing that again. Great. I had this issue earlier. Let's see if we can fix it with our indexing. All right, we're getting close. Let's see. It's very finicky, so you just gotta play with it a little bit. Doesn't like the indentation. Okay. No. So that's close, but I don't like how. So let's see. So it's calculating it, but I don't like how condensed this is. So let's just play with it a little bit and see what we get. It looks really close. I think it should be fine. Yeah, I think that looks good. Okay. So we're going to go ahead and just move on and use our modulo function in our if and statement. Hold on. Yeah, let's just go ahead and put in our modulo function and if then statement to increase our time increments. So we're going to say for I divided by 100 is equal to 0, then it's true. Okay. I'm just if statements. Yeah. And this should increase our uninspected indent. Huh. What's this? What they don't like? Sometimes you just need to play with your indentions. We type this, show maybe if we run it all. No, we're still having errors. Let's look at this real quick. Okay. Never mind. That can't help us. Alright, let's take this expression away real quick and see if that function's still working. Okay, well, we needed, this is a lot better. So this is looking a lot better. I wish I could truly explain to you how I fixed that, but really I was just playing around with my indentions. It seems to like that better. So we're just going to try a different placement for our if-then statement. I divided by 100. Here, that's true. Let's see if that works. No, it does not like that either. Well, let's see. Double parentheses. Maybe if we count. Unindent does not match any outer indentation level. Okay. Okay. Alright. See if that works. Okay, perfect. Great. Alright, so we just used our modulo if-then statement to increase our time segments or spatial steps. So in our calculations using our expression, so we're going to go here and play with this change in time real quick. See if this is stable or not. So just do 0.8. See what that does. Okay, yeah. So really wonky, very unstable. If you have a big change, let's say we have a smaller change. We'll just do 0.51 and see what that does to stability. All right, so so a very, very small change. Well, that's not very small, but a small change still affects it. Let's see, 0.01. Let's see. Yeah, okay. Yeah, so this is showing that it's very unstable. Um, yeah. So yeah, it's just so we're getting so we had stable results at specific values of the discretization, and you see now that we changed our change in time increments by little, and showing instability, in which in our next video um, we will apply the Newman stability analysis that we are required to keep this stable in our code. So yeah, we're done with this one, and we'll move on to part 4.